Alright, today we're going to continue on with section 9.1, where we're going to be trying to further understand properties of angles and learn about angular and linear velocity. So the first thing we're going to talk about are supplementary and complementary angles. So this is something that should not be new to you, but we'll redefine them. So two positive angles, alpha and beta, are complementary if their sum is 90 degrees or pi halves if we're dealing in radians. Another key thing to point out is that they have to be positive angles. That'll come into play down here when we actually find some of these. Two, again, positive angles, alpha and beta, are supplementary if their sum is 180 degrees or pi. So now let's do a few examples. We want to find the supplement and the complement of these four angles. Another real quick thing to point out that you see I have starred here. Remember, complements and supplements do not have to share a common side, so they don't have to be right next to each other. It can be two random angles in space, and they could still be complements or supplements as long as they meet our definitions of complementary and supplementary angles. Okay, so now back to the examples. So I have 40 degrees, 150 degrees, 3 pi sevenths, which we're assuming is radians, and 2, which we're also assuming is radians because they do not have degrees there. So I want you to pause the video, find the complement and the supplement of each of these. If for whatever reason it does not exist, then just write none. So unpause the video when you're ready to check your answers. Okay, so for 40 degrees, we want to think, okay, well, 40 plus what equals 90? So 40 plus 50 equals 90, so the complementary angle is 50 degrees. The supplementary angle is 140 degrees because 140 plus 40 is 180 degrees. For 150 degrees, there is no complementary angle. Nothing plus 150 equals 90. That is a positive angle. So again, that's why that definition of two positive angles is important. 150 plus 30 is 180 degrees, so that is the supplement. Down here for C, so the complement, I want to think about, okay, well, I know 7 pi sevenths is pi. So I know 3.5 pi sevenths is pi halves, but I don't like to have a decimal in the numerator, so instead of writing 3.5 pi sevenths, I'm going to convert this into pi 14ths. So I know 3 pi sevenths is 6 pi 14ths. So I know 7 pi 14ths is the same as 3.5 pi sevenths. So 6 pi 14ths plus pi 14ths is going to be 7 pi 14ths. So pi 14ths is going to be the complement. It would also be the same as 0.5 pi sevenths, but again, I don't like to write a decimal in the numerator. So I'd rather write, it's more proper to write pi 14ths. The supplement, on the other hand, again, I know that I want it to add up to pi, so if I have 3 pi sevenths, then I need to add 4 pi sevenths to make it 7 pi sevenths. So the supplement is 4 pi sevenths, the complement is pi 14ths. Over here for D, 2 is larger than pi halves. Remember, pi halves is approximately about 1.57, so 2 is not going to add to anything to make it pi halves, or at least nothing that's positive, so there is no complement. The supplement is going to just be pi minus 2. I could type this into my calculator, but I don't need to. It's actually kind of just nicer to have an understanding that it's pi minus 2. Alright, next thing we're going to look at are converting angles from degrees, minutes, seconds to decimal degrees. We're just going to use our calculator for this. It's not really worth doing by hand, and when you're doing it by hand, half the time you're using a calculator to assist you anyways. So how we do this in our calculator, if we want to use our calculator, the degrees symbol is if we do second angle and then the first choice, the minute symbol is if we do second angle and the second choice, and the seconds symbol is if we do alpha plus. And so I'll demonstrate that for you now. So here, if I have 85 degrees, 18 minutes, and 30 seconds. So this converted into 85.308 degrees, and then negative 125 degrees and 36 seconds converted into negative 125.01 degrees. So now I'll show you on the calculator how I got that. So to type this in, we type in 85 and then we do second angle, and then again the first choice is degree, and 18 minutes, so we do 18, second angle, the second choice is minutes, and then we do 30 seconds, so 30, and then alpha, and then this is what I was talking about above the plus sign, you see the little quotations, that's the seconds symbol. So now we have 85 degrees, 18 minutes, 30 seconds. We hit enter, and that's how I got the 85.308 degrees. Then we can do the negative 125 degrees. We need to put in 0 minutes, so 0 minutes, and then 36 seconds. We hit enter, and that's how I got the negative 125.01 degrees. So that's where those answers came from. Now the next thing we're going to look at is what if we want to go the other direction. So what if we have decimal degree but we want to turn it into degrees, minutes, seconds? It's even easier on the calculator. So we're just going to plug in the number, not writing the degree symbol, and then hit second angle, and then the fourth choice down is DMS. So if I have 642.54 degrees, I pull out my calculator, I type in 642.54. I do not put in the degree symbol, I just go right to second angle, and then the fourth choice down is DMS. Hit enter. We get 642 degrees, 32 minutes, and 24 seconds. Over here, if I have negative 46.52 degrees, so we'll type in negative 46.52, second angle, and then the fourth choice down, and we hit enter. So we get negative 46 degrees, 31 minutes, and 12 seconds. Alright, now quickly I want to show you a little demonstration to get a better appreciation for the relationship between degrees and radians. And radians both in terms of pi and in terms of just a number. So here you can see I have this angle, it's at 60 degrees, which is pi thirds, or 1/3 pi. That's the same as 1.047 radians. So both this measure here, 0.33 pi, and 1.047 are the same thing. This is just in terms of pi, this is in terms of a number. And we can see that, another way to think about this is 60 degrees is almost 1 or approximately 1 radian. It's a little bit more. And we can see if we just rotate this whole thing, we can see how the numbers change in terms of pi and in terms of radians and in terms of degree. So I can see as this gets close to right there, which should be 90 degrees, so I went a little bit past, but again, we can get the idea. So at approximately 90 degrees, I'm at approximately 0.5 pi, and that's 1.5 radians approximately. It's like 1.54, but we get the idea. And if this continued on, we can see that once it gets to closer to pi, so again I went a little bit past, but this is approximately 180 degrees, so it's approximately 1 pi, or we think of pi as 3.14. I'm a little bit past, so I'm at 3.177. But hopefully we get the idea. If I deal with negative angles, so here I'm at almost negative 720, that's at almost negative 12.59 radians. If I go to positive angles, here I'm almost at 1080 degrees, so I'm almost at 18.589 radians. And so again, it's just to get an appreciation for the relationship between degrees and radians. Alright, now let's look at an example understanding the relationship between arc length, radius, and angle. So we want to find the distance between Johannesburg and Jerusalem. We're going to assume that the Earth is a sphere of radius 6,738 kilometers, and the cities are on the same longitudinal line. So one city is due north of the other. So if I have Johannesburg, South Africa is 28 degrees 8 minutes south, and Jerusalem, Israel is 31 degrees 46 minutes north. I want to find the distance between the two cities. So I need to use my equation, arc length, which is going to be distance, equals radius times central angle. So I want you to pause the video and try to find this distance, and unpause it when you're ready to check your answer. Okay, so you can see I did a rough sketch on this globe. It's obviously not to scale, but I kind of drew the equator in here, and I know Johannesburg is south of the equator. That's why it's 26 degrees 8 minutes south, and Jerusalem is north of the equator, so it's 31 degrees 46 minutes north. So the total central angle between those two is going to be the sum of those angles. So 31 degrees 46 minutes plus 26 degrees 8 minutes is 57 degrees 54 minutes. So now if I'm using this equation, I know my radius is 6,738 kilometers, and I have a central angle of 57 degrees 54 minutes, but I need to turn that into radians in order to use this equation. So I multiply that by pi over 180. So I typed this into my calculator exactly as it's written here, and I end up with 6,809.06 kilometers. Alright, now we're going to look at another application of this, and that's going to be speed. So if we consider a circle of radius r, if s is the length of the arc traveled in time t, then the speed of the object is going to be what? Well, we know that speed is distance over time, so in this case distance is arc length. So it's going to be arc length over time, or s over t, where remember s is arc length, that is not speed. This type of speed is what we call linear speed. So think about, how fast an object is traveling. So like a bicycle or a car is going to have a linear speed, but it has to do with the wheels turning. So that's our arc length and our revolution. Then we also have what we call angular speed, and angular speed is the speed at which the central angle is moving. So if you think about this, angular speed is not going to relate to, we're not going to be affected by the radius, whereas linear speed is. Angular speed, again, is just going to be affected by how quickly the angle is changing. So let's look at an example. So a car is moving at a rate of 40 miles per hour, and the diameter of its wheels is 2.4 feet. Find the rotational speed of the wheels in revolutions per minute, and find the angular speed of the wheels in radians per minute. Okay, so in order to do this, we need to understand that this 40 miles an hour is a linear speed. So think, if you've taken chemistry, basically you just need to do a bunch of unit conversions. So I want you to pause the video and try to convert 40 miles per hour into revolutions per minute, and then into radians per minute. Unpause when you're ready to check your work. Okay, so here you can see my work and what I was talking about by just converting units. So I start with 40 miles per hour. I need to change miles into revolutions, and I need to change hours into minutes. So first I convert miles to feet. So I multiply by 5,280 feet over 1 mile. Then I multiply by 1 revolution over 2.4 pi feet. This is the circumference of the wheel. And then I multiply by 1 hour over 60 minutes. And so I end up with 466.854 revolutions per minute. Then to go to radians per minute, I just have one more conversion. I have to convert revolutions to radians. I know there are 2 pi radians per revolution, so I multiply by 2 pi over 1, and I get 2,933.333 radians per minute. Last example, I want you to find the angular speed in radians per second and how fast the roller is moving across the lawn in inches per second, so that's the same as saying find the linear speed. So pause the video and unpause when you're ready to check your work. Alright, so for each one of these, it's just 2 simple conversions. I multiply 1 rev over 5-6 seconds times 2 pi radians over 1 revolution to get 7.540 radians per second. And I multiply 1 revolution over 5-6 seconds by 30 pi inches over 1 revolution, and we get 113.097 inches per second. Here's your conclusion.